Welcome to the second lecture on the course Introduction to Mobile Robotics. Today we are going to see the different classifications of mobile robots. In this presentation, we'll first review the main locomotion modes of mobile robots, wheeled, legged, and aerial, and then the focus is in depth on legged robots and wheel robots. Legged robots and wheel robots are the fascinating area of robotics. Let's begin with the categories of mobile robots. Mobile robots move by various means. Wheeled robots use wheels or tracks and are great for smooth floors. Legged robots use jointed legs, like an animal, letting them walk over rough terrain. And aerial robots, like drones, fly in the air. All three types, wheels, legs, and flying, are common in mobile robotics. Here are the three main categories: wheel robots, leg robots, and aerial robots. Wheel robots, which are fast and simple on flat surfaces. Leg robots, which step and adapt to uneven ground. Aerial robots, such as drones, which navigate in three dimensions. They have propellers or wings to fly. Each has strengths. Wheel robots excel on roads and factories. Leg robots handle complex terrain, and aerial robots reach inaccessible places. Now we'll focus on the leg robots. By definition, they use articulated limb mechanism for movement. Think of them like robotic animals or humans. The big advantage is versatility. Leg robots can climb stairs, step over debris, and traverse sandy or rocky ground that wheel robots cannot. However, this advantage comes with the complexity. Each leg has multiple joints and motors, which makes the machine heavier and more expensive and more power hungry compared to simpler wheels. Stability is a key concept for leg machines. In general, the more legs a robot has, the more stable it can be. For example, 8-legged spider leg robots have very wide support and great balance. Another term that very important in leg locomotion are the gaits. Gaits, which are the repeating patterns of leg movements. Each gait is defined by which legs are on the ground at each moment. To walk safely, a leg robot must keep its center of mass within the support polygon formed by its feet on the ground. For example, when a hexapod lifts three legs to step, the other three form a triangular support polygon. Control of leg robots involves planning of foot placement and coordinating joints so the center of mass stays within that polygon. Again, repeating the term gait. A gait is a sequence of lift and release events. For a robot with k legs, the number of events n is defined by n is equal to 2k minus 1 factorial. For example, if we have a biped walker, that is one that is having two legs, the number of possible events is n is equal to 2k minus 1 factorial, which is equal to 6 possible events. In such cases, the different events are lifting the right leg, lifting the left leg, release the right leg, release the left leg, lift both legs together, and release both legs together. Now we'll see the classification of the leg robots based on the number of legs. One-legged hoppers must balance on a single point. Two-legged bipeds must constantly balance forward and backward. Four-legged robots, like a dog, can use three-leg tripod gait to stay very stable. Six-legged robots, hexapods, can always keep at least three legs on the ground, giving excellent static stability. Consider a classic example, Rybert's Hopper, a one-leg robot from the 1980s. It looks like a pogo stick and moves by hopping. By compressing a springy leg and then releasing it, it can hop vertically or lean to hop forward. Rybert showed that even a single leg robot can balance dynamically and control its motion. The hopper's control system adjusts the body's position between hops to keep balance, demonstrating principles of dynamic stability in legged locomotion. Another example is the Sony Aibo robotic dog, a four-legged quadruped robot slide. As a quadruped Aibo walks like a dog or cat, it typically moves in a trotting pattern, lifting two diagonal legs at a time. With four legs, the robot can always keep three legs on the ground, which gives it a very suitable tripod support. Aibo was designed for home environments. It's like allow it to climb small obstacles and maintain balance on uneven floors. Its onboard sensors, cameras, and force sensors, and sophisticated control software coordinate the gait and enable behavior like running, sitting, and even playing saucer. Two more hexapod examples, Genghis and Lauren 2. Genghis, developed in 1980s by Rodney Brooks, is a six-legged insect robot that can crawl and turn using simple neural network control. Lauren 2 is a biologically inspired six-legged robot that can climb and adapt its gait. Its design is based on stick insect, hence the name Lauren. Both use legs, which means at least three legs can stay on the ground as it walks. This hexapod configuration provides high stability and redundancy. If one leg fails, the robot still stands. Coming to the two-leg robots like Honda's, Asimo's, and Vabian. They climb the stairs and navigate human environments by imitating human gait. They require an active balance control. For example, Asimo uses zero moment point theory, continuously adjusting so its center of mass stays within the support area. Advancement allows running, quick turns, and agile movements in these humanoid robots. Four-leg robots, which we have already discussed, that it includes four legs, or we call it as quadrupeds. Examples include Bloston, Dynamic Spot, and MITS Cheetah series. These robots have combined legs and can trot, pace, or gallop over terrain. MITS Mini Cheetah, which is around 12 lb, is springy and agile. It trots quickly over uneven ground and can even perform backflips. Four legs provide good speed and stability on challenging terrain. Six-legged robots, which has six legs inspired by insects like cockroaches, ants, etc., offer inherent stability, always at least three legs on ground and a variety of gaits. Robust against leg loss. Example, if one leg fails, others keep the robot upright. Examples, as I already discussed in the previous slide, mit- mighty leg laps Genghis and Dela's Lauren too. They exhibit stable walking gaits and can climb obstacles by coordinated leg movements. Now we'll see the limitations of leg robotics. Leg robotics excel on difficult terrain, but at a cost. They are mechanically complex, with many motors and joints, so they are heavier and more expensive than single wheel robots. They also consume more power, since each leg motion requires lifting and pushing the body up and over obstacles. Their maximum speed is usually lower on flat ground compared to wheel vehicles. Control is challenging. Keeping balance, especially for bipeds, requires precise sensing and fast feedback control. In short, leg robots trade off efficiency and simplicity for terrain versatility. All these factors, complexity, energy needs, and control difficulty, are important limitations to keep in mind. Now we move on to the wheeled mobile robots. In this section, we'll introduce mobile robots, which represents the most widely used form of mobile robot locomotion. Wheel robots are particularly popular because of their mechanical simplicity and high energy efficiency. Unlike leg robots, wheel robots maintain continuous contact with the ground, which simplifies balance and control. They are commonly deployed in structured, human made environments such as factories, warehouses, and roads. A classic example is autonomous road vehicles such as the NavLab series, which demonstrate the effectiveness of wheel locomotion for long distance navigation. Because of these advantages, wheel robots form the backbone of many real world mobile robotic systems. Why wheels are popular? Wheels are one of the earliest and most efficient mechanisms developed for locomotion. In mobile robotics, wheels are popular because they eliminate the need for complex balance control. Since all wheels typically remain in contact with the ground, the robot does not have to constantly adjust its center of gravity, unlike leg robots. This leads to smoother motion, lower energy consumption, and simpler control algorithms. Wheel robots also experience less mechanical wear and tear compared to leg robots. As a result, they are ideal for applications where speed, efficiency, and reliability are critical, such as automated warehouses and autonomous vehicles. Now we'll see the basic wheel types. There are four types: standard wheel, caster wheel, Swedish or omni wheel, and finally the spherical wheel. The images of the different wheel types is shown in this slide. Now we'll see in detail each design for the wheels. Standard wheels and caster wheels. Standard wheels and caster wheels are widely used in simple mobile robot designs. Standard wheel provide propulsion and directional control, but require steering mechanism or differential drive for turning. Caster wheels, on the other hand, are passive and do not provide propulsion. Instead, they support stability and allow smooth changes in direction. Many indoor robots, such as service robots and small research platforms, use a combination of standard drive wheels and caster wheels to achieve a balance between simplicity and stability. The next type are the Swedish and spherical wheels. Swedish wheels are also known as omni wheels, are designed to allow lateral movement in addition to forward motion. This is achieved using small rollers mounted around the wheel circumference. Robots equipped with Swedish wheels can move in any direction without changing orientation, making them omnidirectional. Spherical wheels extend this concept further by allowing unrestricted movement in all directions. However, both Swedish and spherical wheels introduce higher mechanical complexity and control challenges and are therefore mainly used in specialized applications requiring high maneuverability. Wheel geometry and arrangement. Wheel geometry and arrangement play a crucial role in determining a robot's stability, maneuverability, and control characteristics. There is no single wheel configuration that is optimal for all applications. Factors such as the number of wheels, their placement, and whether they are driven or passive must be carefully considered. For example, fewer wheels reduce mechanical complexity but may compromise stability, while more wheels improve stability but increase design complexity. Designers must therefore select a wheel arrangement based on the intended operating environments. The three wheel configurations. The three wheel configurations are commonly used in indoor mobile robots. A typical design consists of two driven wheels and one passive support wheel. This arrangement allows differential drive where the robot turns by varying the speed of the two drive wheels. Three-wheel robots offer a good balance between stability and maneuverability, making them popular in research robots and educational platforms. However, uneven weight distribution can affect traction, especially on sloped surface. Four-wheel configurations. Four-wheel configurations provide improved stability compared to the three-wheel designs. These robots may use front-wheel drive, rear-wheel drive, or all-wheel drive systems. Four-wheel robots are well suited for outdoor environments and uneven terrain, especially when combined with suspension systems. While they offer better load carrying capacity and stability, steering mechanism become more complex, particularly when all the wheels are driven. And we also have the six-wheel configurations. Six-wheel configurations are commonly used in robots designed for rough or uneven terrain. With more wheels in contact with the ground, these robots achieve higher stability and better weight distribution. Six-wheel designs are often used in planetary rovers and exploration robots where terrain conditions are unpredictable. However, increased wheel count also leads to higher mechanical complexity and more sophisticated control requirements. Next, we'll see the key characteristics of wheel robots. To summarize, the wheel robots are characterized by higher energy efficiency, mechanical simplicity, and ease of control. They perform best in structured environment with relatively smooth terrain. However, their main limitation is poor obstacle climbing capability compared to legged robots. As a result, wheel robots are ideal for applications such as logistics, transportation, and autonomous driving, while legged or aerial robots are preferred for highly unstructured environments.